We'll talk about one theorem that I learned when I was in high school and a seemingly miraculous method to solve it, which is my favorite thing from the training for the International Math Olympiad back in Bulgaria. The theorem is called Ptolemy's theorem, and the method, well, wait a few minutes before we get there. Well, let's start with something that everyone knows. What is the theorem, Brady, that you think everyone knows in geometry?
Pythagoras.
Absolutely. Well, what do you know about it?
Even I know this one. A squared plus b squared is equal to c squared.
All people know this theorem, but do they know how to prove it? So Ptolemy's theorem is somehow related to this one. So who do you think is stronger, Ptolemy or Pythagoras?
Stronger.
Stronger. They're both Greeks.
Well, Pythagoras is more famous.
That is true, but they have to compete with each other, and we shall see. I need another brown sheet.
Already?
Yeah. So we're going to draw a large circle. We need 4 points on this circle. They form a so-called cyclic quadrilateral. It just means they lie on a circle. And you can also draw the diagonals. So what could Ptolemy tell us about these 6 segments? It's very beautiful. It says, if you multiply the opposite sides and add up those products, you will get the product of the 2 diagonals. So AB times CD plus AD times BC must be equal to the product of the 2 diagonals AC times BD. And this is what Ptolemy's theorem tells us. And it doesn't matter where those points are on the circle, as long as they're in this order, it's gonna work. So this is a property about points on a circle. Now, let's see. I said that Pythagoras and Ptolemy's are related. Who's stronger? If I can prove Pythagoras knowing Ptolemy's theorem, then Ptolemy's is stronger.
Okay, so it would be like a parent or a...
Yeah, so Ptolemy would be a parent of Pythagoras. Is this possible? Certainly. So if I draw a right triangle and then take exactly the same triangle and flip it over, what kind of a shape do you think, Brady, I'm going to get?
A rectangle.
It is precisely a rectangle. So we have a B, C, D for the vertices. Now, a rectangle is a very symmetric figure. It has all right angles, obviously. So its 2 diagonals also happen to be equal then. Moreover, their intersection, O, is at equal distances from each vertex.
So they must be on a circle, those points.
Exactly. But as soon as we have 4 points on a circle, guess what happens?
Ptolemy, you say?
Yes, Ptolemy would kick in.
Right.
So now let us backtrack a little bit. We started with the right triangle. Let us name its sides, A, B, and the diagonal will be C. Okay, but then this side should be A, and this side should be B, and the other diagonal should also be C. Let's hit this picture with Ptolemy's. So what do we have? The product of the opposite sides, A times A, plus the product of the other opposite sides, B times B, must be equal to the product of the 2 diagonals, C times C. Does this look like a theorem we've seen before?
It looks good.
That is precisely the Pythagorean theorem, which means that Ptolemy is stronger. Pythagorean theorem is a special case of Ptolemy's theorem, but Ptolemy's theorem can do a lot more. And so we create a new method today, actually I've known about this method for a long time, that will solve Ptolemy's theorem. So actually Ptolemy's can be proven in many different ways. If you Google, you will see lots of different proofs. You will see a proof in plane geometry, which is beautiful but very tricky to come up with. You can see technical proofs using trigonometry, who likes those, or using even complex numbers, very sophisticated. But none of these approaches really shows the true elegance and simplicity of Ptolemy's theorem. None of them shows you why it is really true. The new method that we will talk about today, called inversion in the plane, looks originally like a mysterious black box, because it will turn our circle in Ptolemy's situation into something that a third grader can tackle. So it will turn this whole picture into something very simple. Only 3 points that are lined up, A1, B1, and C1. What could a third grader tell me about this picture? What is true, Brady?
A and B, and then B and C makes the whole line.
Correct.
Yeah.
If I add the two shorter ones, I must get the longer one. Look back at Ptolemy's theorem. We are almost doing something similar. We're adding two things and getting a third one. Could indeed this be the same situation but in a different world, in an inverted world? And the answer is yes. So what is inversion? Inversion is obviously some transformation of the plane. It's some points to some other points. So let's think about other transformations in the plane that we all know. So what would be one that you, Brady, have heard about?
Like reflections and things like that. Is that what we're doing?
Correct, yeah, you can reflect across a line. Yeah, that's a perfectly good transformation. How about this one? That's called rotation about a point, definitely. And how about this one? That's called translation. And there is another one when you click on a map to expand it, to zoom it out or zoom in, that's what's called a rescaling or dilation. So suppose I draw an elephant. What do you think will the elephant look after each of those transformations? Would it look like a rabbit or would it look like an elephant?
Yeah, it will keep its elephantness.
Correct.
Yeah.
It may kind of flip-flop, but it will still look pretty much like an elephant. Well, our inversion is a completely different animal, because we saw how it transformates a circular picture into a linear one. So it must do something horrible to shapes. If you take your nice elephant and hit it with that inversion, what will turn out in the end is something that might look like Aladdin's shoe from the movie. Completely ridiculous. So we need to have control over the situation. What is going on? So for an inversion, you need a circle. And you're the boss. You can draw the circle anywhere in the plane you like and as big as you like. And we mark its center, O. Let's say we take a point outside of this circle, X. Where will this point go? It's like a small algorithm here. We start at a point X. We connect it with the center. We draw a tangent through X until it hits the circle at T. And then we drop a perpendicular to OX. So our point X, if it is outside of the circle, will travel into the circle into x1. This actually can happen on any point in the plane. For instance, if I take something very close here and we just repeat, we connect it to O, we draw a tangent, and we drop a perpendicular. That will be where y1 will go. If I take any point outside the circle, where do you think it will go?
It looks like it will go inside the circle.
Correct. That can happen to any point outside the circle. Now, we have more points to worry about. What happens if you start with a point inside the circle? Well, we want to be consistent. So the logical thing is to reverse this algorithm. If I take a point Z, well, I still need the ray through Z and O because everything important looks like it's gonna lie there. But then I have to backtrack and erect a perpendicular at Z to this ray, hitting the circle, and finally drawing my tangent to the circle until it intersects our original ray in point Z1. So if you start inside the circle, you go outside of the circle. That's what inversion does to you. Okay, I think we're still missing a few points. Which points did I not talk about?
All right, the ones on the circle.
Correct. So suppose I take a point, how about U? So U is on the circle. I'm going to treat it as if it is a point outside of the circle. So we're going to apply our first algorithm. We connect it to O. Next, if you remember, I'm supposed to draw a tangent to the circle through that point. Oh, okay, well, the point is already on the circle, so it's just kind of easy. And the tangent will intersect the circle in our next point. Oh, but that's point U already. Okay, and next I have to drop a perpendicular to my line until it intersects that ray. Okay, I'm going to drop a perpendicular to this line, but I'm already there. So I literally have not moved from U. So any point on the circle is going to go into itself. And that kind of makes sense. You will take outside of the plane, this infinite plane, and you will squash it inside. You will take the inside, you will spray it outside, spread it all over, but the points on the borderline are gonna stay fixed and not gonna move anywhere. What happens to the center? The center looks like it's an inside point, so we should apply our second algorithm. But can it possibly work? That center is a very strange point. So the first thing we have to do by our second algorithm, if you remember point Z, we need to connect it to the center. Well, how do we connect it to the center? It's already one point.
Yeah, how do you draw that ray?
I don't have a ray here. So we are already kind of stuck with our algorithm. But maybe you'll say, it doesn't matter which ray. Let's just draw a random one. Okay, there you go, no problem. Next, I'm supposed to erect a perpendicular, certainly, no problem. I'm supposed to draw a tangent to the circle until, we are in trouble.
It's parallel.
They're parallel. There is no way these two lines are going to intersect. So you may say, oh, it goes somewhere at infinity. Okay, in that direction, but what happens if I chose a different direction? It's going to go in that direction at infinity. For our purposes of proving Ptolemy's theorem, we don't need to even bother with the center of inversion. We will not define inversion at the center. And you're asking, oh, that doesn't seem right. It should be defined everywhere. Beg your pardon. If you, for example, know anything about functions, one of the first functions that would look like this is f of x equals to 1 over x. Brady, can I plug in any number here? I think we're in trouble.
Can't put 0 there.
We can't put 0 there, so this function is not defined at 0. But it's a perfectly good function and you can see it all over the place. So why not leave inversion not defined at the center? Now, when I was in middle school, they used to tease us with the following question. How can you catch all lions in Africa?
I don't know.
All right. Well, build a fence, a really strong fence around the circle. Where would you like to stay, Brady? Outside the circle or inside the circle?
I want to be free on the outside.
That's where the lions are. So you're going to make sure that inside the circle there are no lions.
I thought I was a lion.
Ah, well, okay.
All right, I want to be out. I want to be away from the lions. Okay.
So you stay inside this lion-free circle, and then you hit the world with inversion. So all the lions are outside, they'll come in, but you will be safely outside and observing them. Well, I don't know if that's a worthy goal, but you see the excitement of 5th graders, how much they could foresee the power of inversion. What are the basic properties of inversion? We already saw a few of them. Points outside the circle go in, points inside go out. But do they do this randomly? What happens if I apply inversion twice in a row? So point x from the outside is going to go into point x1 on the inside, but if I do this once again, I'll simply reverse my algorithm and go back to x. So what happens is that points in the plane are sort of married. and they flip-flop from inside and outside. They have their chosen partner, and all they can do is flip-flop. The only points that are singleton are those on the circle. They stay put. And O, we don't touch it. We agreed. So applying inversion twice in a row will simply not do anything to the plane. It will keep the points wherever they are. This is super important because if you take your elephant and invert it to Aladdin's shoe, what would happen to Aladdin's shoe if you hit it with inversion? It will come back and resurrect itself as the elephant. I need another sheet.
All right, you got it. You're going to ruin these bowls.
We saw that Ptolemy's theorem was originally situated on a circle, but miraculously that was turned into a line. Now, I want to know what happens to lines in the plane, but now some lines will be more special than others. Some lines will go through the center of inversion, and other lines will go not through the center of inversion. And different things will happen to them in each case. Now let us look at the first case where they go through the center. If I take a point outside on this line, it will go inside this same line.
To its twin.
Exactly, and they will flip-flop. The outside part of this line will go inside, and the inside is going to go out. And the points on the circle will just stay put. Of course, we said we're not going to touch the center of inversion, so we don't care about it. But by and large, they go to themselves. So they will still be lines, exactly the same lines. You're not going to see any difference before and after inversion.
So if I took all the points on the line and inverted them, I would draw the same line?
Exactly. Well, that's pretty. Nothing happened to that line. But if the line is outside the circle or inside, but most importantly not going through the center of the circle, something wild is going to happen. Let's experiment. So I'm going to take a point X on this line, connect it to the center, draw a tangent, drop a perpendicular. All right, well, so far no surprises. I knew that X was going to go inside the circle. But let's experiment more. Now I'm going to take another point, Y, draw a tangent, and drop a perpendicular. This is Y1. So far, I don't see any surprise. Do you think this line is going to go into a line here? Could it possibly go into a line? I don't think so. Because there is no line inside the circle. It's going to be just a line segment at best. But is it a line segment? Let us experiment. We have Z, draw a tangent, and drop a perpendicular. Oh, we already see that the points inside the circle are not anymore lying on a line. On what shape do you think, Brady, they lie?
I reckon I can guess now.
Yeah, guess.
Well, I reckon we're going to get a circle.
Yes, but what kind of a circle? Circles are of two types. They either pass through the center of inversion or they don't. What is your guess? Will our circle pass through O or will it not?
I think it... Oh, I don't know. Because you told me O doesn't map to anything, so...
O actually matters a lot. We just don't touch it.
Yeah.
It's like the king who does not participate in the battle but only oversees what's happening.
Okay.
Now, I can draw maybe one more point, but let's try to draw it far away from O.
Okay.
Maybe that will give us a clue.
Yeah.
What happens to points that are far away from O? Where do they go under inversion? Close to O or far away from O? Now, remember those lines in Africa? The further away the lines are from our fence, the closer to something they will go. I am getting close to O. Closer and closer and closer. And you can go infinitely far away, and you're going to get infinitely close to O. So actually, if you continue doing this, you will clearly see a shape of a circle. Now, of course, my picture is drawn by hand, so it looks more like an ellipse, but definitely you can see that that's not a line. So it is a theorem that a line that does not go through the center will map to a circle that goes through the center.
Okay.
And that is fundamental. Now, whew, It looks like we still need a lot of ground to cover, but do we? Now, how many circles are there with respect to inversion? 2. They either pass through the center of inversion or they don't. But I already have one that passes. It's right here. What do you think, Brady, happens if I hit that circle with inversion?
You'll get your line back.
Exactly. Absolutely. Because doing inversion twice is going to get us back where we started. Let us summarize so far. Lines through the center go to themselves. Lines not through the center go to circles through the center. And conversely, circles through the center go to lines not through the center. Are we missing one type of figure here? I think we are. And this is circles that don't go through the center of inversion. A circle not through the center of inversion goes to another circle not through the center of inversion. And in fact, that's a theorem, and it can be proven using pairs of similar triangles, just like any of the other theorems in this talk. We know properties of inversion. Now we're back to Ptolemy's theorem. Let's see if we can prove it at our first attempt. So what I have here is our cyclic quadrilateral, in other words, 4 points on a circle, and we are trying to prove something about the sides and the diagonals, as Ptolemy's theorem says. We want to simplify this picture. How can we simplify? Obviously, lines are preferable to circles. They are simpler to work with. Can I turn this circle into a line? Yes, with inversion, but I need to choose my center of inversion very carefully, because different circles will go to different figures. If you remember, if a circle doesn't pass through the center of inversion, it's just going to go to another circle that doesn't pass through the center of inversion, and that's no use to us. However, if a circle passes through the center of inversion, it's going to miraculously turn into a line not through the center of inversion. So where should the center of inversion be if I want to make a line out of this circle? What do you think, Brady?
Wow, you've got infinite options.
Yes, but there is one place where it must be. It must be somewhere on the original circle for Ptolemy, so that the original circle passes through the center of inversion.
Yeah.
All right, so let me just take something symmetric here. Looks, oh, excellent. Now, you are thinking I should draw the circle of inversion. I don't have to. Actually, all I care is about the shapes of figures after inversion, not exactly where they are located. So at any rate, this circle through the center of inversion will turn into a line not through the center. So I can just be bold and draw a line not through the center of inversion and declare that my circle goes there. Why not? Now we want to quickly figure out where do the points A, D, C, and B go. You may be thinking, well, now I need the circle of inversion in order to do all of these tangents and all of these perpendiculars. No, we can be efficient. We can apply a little bit of logic. For instance, take point B. I know that point B has to go somewhere on this line because it is on our blue circle. Okay, so it has to be somewhere. But also I know that it lies on a ray OB because that was our first step of the algorithm for inversion. So it has to lie both on this ray and on our line L. So I think we figured out it's here. And the same way, we can efficiently find the images of the other points. So our cyclic quadrilateral now gets flattened onto a line. And I do want to give a warning here. I'm not saying that the sides of the quadrilateral become line segments. No, they will actually become arcs of circles, most likely. I am saying that the vertices are now lined up on a line. Brady, do you think that's really the best we can do with inversion? Because a while ago, I promised that inversion will make this picture look something that a third grader can cope with. 3 points on a line, and then we are adding up the two shorter segments to get the bigger one.
Well, I mean, you've got 4, so you could do...
That's not for a third grader.
No.
Now, there are too many segments floating about here.
Okay.
We really want simplicity and elegance.
Okay.
So we have to go back again to our choice for the center of inversion. Even though we are on the right track to choose it on the original Ptolemy circle, we were just a little bit too sloppy where exactly to place it. If I want to eliminate one of those points, where should O be?
On one of the points.
Exactly, because we're not going to even touch it. We're going to leave it there and forget about it as our center of inversion. So since we promised we're going to end up with points A1, B1, C1, which point shall we lose?
Well, D.
D, that's right. That is exactly where we want to place our center of inversion. Now we have to cut, and I have to draw another picture because I cannot, this is too complicated.
It's too messy.
Our first attempt failed, but we don't give up. The blue circle is now going to go into a line L, but we have only 3 points to map, points B, C, and A. So we've got A1, B1, and C1. Okay, great. So that was what inversion promised us. We can get it to this simplified situation. And we do know that if I add the length segments, the two shorter ones, I'm going to get the longer one. A1, B1 plus B1, C1 is A1, C1. So what? Did we talk about what happens to distances on the inversion? No, we didn't. But I actually need exactly to know what happens to the old distances. Here I have 6 of them that participate in Ptolemy's theorem in terms of the new distances.
Like how have they scaled?
Exactly. And we know that inversion is not like dilation or rescaling of the plane. It does actually quite horrible things to points. For example, if you have 2 points that are very close to the center of inversion, each of them is going to be mapped very, very far away, and that will enlarge the segment drastically. So we need to derive a couple of formulas that will tell us exactly what happens to distances on the inversion. So let's get started. This is the circle of inversion, a point X outside the circle. There is something that we have overlooked here. There is a segment that is missing. Which one? It is segment OT. That is super important. First of all, it's R long, that's the radius of inversion. But there is another right angle. Every time you draw a tangent, it is perpendicular to the radius. So now when you look at this picture, you see a bunch of similar triangles. There are 3 triangles in this picture, 2 small and 1 large, and they are all similar because they have the same angles. I'm interested only in 2 of them, in this small red one and in the large one. So let us see what they will give us. Triangle OTX1 is similar to triangle OXT. And you can check that the right angles are matching. So what do I need from this? I need a ratio of segments. OT to OX1 is equal to OX to OT. All right, big deal, but you know what? OT is the same and it's the radius. So I can simplify this to multiplying the 2 distances from the center, OX and OX1, to the radius squared, which is OT squared. And this is our first distance formula. In other words, old distance from the center times new distance from the center is always fixed. It is R squared, which actually explains the phenomena why points close to the center are going to be mapped very, very far away. Because those 2 distances, old and new, have to balance each other to multiply to R squared. So if one of them is small, the other one has to be large, and vice versa. Okay, that's formula 1. Now we need formula 2. Right here. So what we have here is another inversion. We really need to know what happens to any segment on the inversion, not just to segments that contain the center. Because we found formulas for those, but not to random other segments. So what we have here is point A that goes to A1 and B goes to B1. If you wonder where the circle of inversion is, it's somewhere like this in between them, but who cares about that? We don't need it. Now again, we see two triangles here. Do you think they're similar? The answer is yes. First of all, they share a common angle. That's good news. And now, what do we know about these distances from the center? We just had a formula. If I multiply OA, OA1, that will be the same as OB, OB1, but that turns into a ratio. OA to OB is equal to OB1 to OA1. Aha.
OB1.
OB1 can OB, right. What we have here is a ratio of sides plus an angle makes two similar triangles. And we can now reap the effects of this similarity.
We can what?
Reap off the effects. Can I say that?
Rip off defects?
Not reap, reap. When you're gathering the harvest, we can, okay, I can...
I'll reap the effects. I get you. Yep, I'm with you.
We can reap the effects of this similarity.
Okay.
First of all, what are the two triangles we are talking about? We have triangle OA1B. One is similar to triangle O, but it's not going to be A, it's going to be B, because the points flip-flop in this ratio. Okay, so now what I'm interested in only is the new distance between the points in terms of the old one. So let's use some ratios. A1, B1 over OA1 is equal to AB over OB. All right, that looks like a mess, but we're gonna resolve it. We're interested in the new distance, A1, B1, so we solve for it. We push OA1 to the other side. We get AB times OA1 over OB. Now this is a complete mishmash of new and old distances. I have new distance, A1, B1. Here I have old distances. I don't like this one, this is new. I want my new distance to be completely expressed in something that happened before inversion, so I have control over it. Can I replace OA1? The answer is yes, because we had our first formula that if I multiply the distances to the center of inversion, this is always r squared. So from here, OA1 will be some ratio of the radius and OA, and we can simply plug it in and get, oh, this looks like a messy formula, but we really need to understand what it says. All right, so it says new distance is equal to its predecessor, the old distance, times always r squared over the old distances to the center. So everything is expressed in terms of the world before inversion. We are ready to finally prove Ptolemy's theorem.
Thank the Lord.
Okay. Brady, you have to be excited how all of this messy stuff actually proves it.
I know you're excited, but you're not the one who has to edit the video afterwards.
I know. Okay, final attempt. We are proving Ptolemy's theorem.
Yep.
But we will apply our distance formula 3 times in the inverted world. Inverted world means really this red line here where everything mapped on the inversion. So we will have A1, B1 plus B1, C1 is A1, C1. Now these are new distances, so we can rewrite them in terms of our formula. So new distances were the old distance times the radius squared over the old distances to the center. But the center is not O, really, it's D. So we will be talking about distances from A and B to the center, which is D. In other words, AD times BD. That alone is A1, B1. And we continue in a similar fashion. We have old distance BC times radius squared, and then distances to the center, which is d. And finally, AC times r squared over distances to the center. Brady, what would you like to do when things repeat?
Get rid of them.
That's right! So what do I get rid of them?
You must be able to get rid of those r squareds.
Correct. We divide everything inside by r squared. And we miraculously understand that the radius of inversion did not matter here. We just got rid of it. Okay, next, who likes denominators? Can we get rid of them too? The answer is yes. We just have to find the common denominator of those three fractions. Now, they do share a few things. I have AD twice and CD twice and BD twice. So we will multiply everything by AD times BD times CD. That's the common denominator. Now, if I multiply this fraction by this product, we will, in essence, cancel the whole denominator, and the only thing that will be left to multiply is CD. So that CD must be multiplied by AB. So we end up with AB times CD. Full stop! Does this remind us of something? AD times CD. We have just multiplied the opposite sides of our cyclic quadrilateral. This looks promising. Let's see if the rest will match. BC from the numerator, what's missing here? I think only AD is missing. AD, BC times AD, opposite sides. And that is equal to AC, one of our diagonals, times, what's left? BD, the other diagonal. We are done. We have just shown Ptolemy's theorem.
Was that easy?
Well, it wasn't an easy proof in the sense of the ideas that were used, because inversion is definitely not easy. And it is not a natural thing that one would just try on the spur of the moment. But the actual computations and the proofs really boil down to similar triangles and operations with fractions, as well as realizing where to take our center of inversion. That was a key point.
It was worth the wait.
Now you ask, is there anything else useful that Ptolemy's theorem can prove? The answer is yes. Not only the Pythagorean theorem follows from Ptolemy's theorem, but a couple of really cool facts. Let's look at them.
No, and I thought we were finished.
Oh, no.
Well, we've come this far. Why not watch the additional footage showing how Ptolemy's theorem reveals a link between pentagons and the golden ratio?
I don't think so. One of those roots is utterly impossible.
We've also got a little bit of extra footage about inversion.
In fact, this kind of property is used very often in solving problems with inversion. Thank you for bringing it up.
And if that's not enough, you can go back and watch Numberphile's classic video about epic circles. Links are in all the usual places on screen, down in the video description.